So in this video, I will be using the Radford-Rice method to derive the equation we need for an nth component flash calculation. So in a flash calculation, it's done in a flash drum, and there's a feed going into the drum of a certain number of moles per second. And I think in this problem, we have a two-component mixture, and we're given that the mole fraction of the first component is 0.4. So in this problem, it's benzene. So if our feed was 10 moles, the amount of benzene would be 4 moles per second, and the amount of toluene would be 6 moles per second. And then in the drum, you have liquid phase and vapor phase down here, and then the vapor phase is pulled out and the liquid phase is pulled out for later steps in a longer process in some chemical manufacturing warehouse. So our flash drum is at a set temperature and pressure, which will be given in the problem. And what we need to do is find the composition and amount of moles of our mixture that's in the vapor phase and the liquid phase. We're first going to take a look at the bubble and dew pressure graph that we created in the last part of this video. And for flash calculations, we will be somewhere in between these two curves. So down here we have all vapor, up here is all liquid. This is the dew point line, and this is the bubble point line. So if we go straight over in our graph, on the right side of this will be our moles in the vapor phase, and on the left side here, this will be our moles in the liquid phase. And so now I'm going to start walking you through the equations that we'll need to start deriving this equation. So the first equation we're going to start with is a mass balance equation, that the total number of moles in the feed is equal to the number of moles in the vapor phase plus the number of moles in the liquid phase. That makes sense because as the feed goes in, it's going to split in between a vapor and liquid phase in our flash drum. The next mass balance equation I'm going to write down is the mass balance equation for our first component, which in this case is benzene. So it will be the mole fraction of benzene times the total moles of our feed will be equal to the mole fraction in the vapor phase times the total moles of vapor plus the liquid mole fraction of benzene times the moles in the liquid phase. Additionally, we are going to be using Raoult's law, which is the liquid mole ratio times the pure component saturation vapor pressure of each component times the vapor mole ratio of each component, or the vapor mole fraction of each component, times the total pressure. And then with this equation, I'm also going to define a new variable called Ki, and that is just the ratio of our moles in the vapor phase divided by moles in the liquid phase. And this can also be rewritten as the saturation vapor pressure divided by the total pressure of the container. So I'm rewriting like this because this will actually be key to the Radford-Rice method. Since we know the temperature and pressure, we will be able to calculate the value for K using this expression right here. So now, to start deriving the equation for the Radford-Rice method, we need to start with the equation that says the sum of all the sum of moles in the vapor phase minus the sum of moles in the liquid phase is equal to 0. And this equation makes sense because the sum of moles in the vapor phase and the sum of moles in the liquid phase are both 1, so 1 minus 1 equals 0. So now I'm going to rewrite this summation. This equation has one summation, so it'll just be yi minus xi equals 0. And then I'm going to rearrange this equation here and solve for the liquid mole fraction, or solve for the vapor mole fraction. And then I can go ahead and plug this value in for yi up here. So then we just get this equation. From there, I'm going to be using this mass balance equation here and rearranging it a little bit so that we can isolate the mole fraction of liquid, or the liquid mole fraction of benzene, and that way we'll be able to get rid of this unknown in our equation. So I'm rewriting this equation here, but instead of using the vapor mole fraction, I'm going to be using this expression right here, using K. So that term becomes the total moles in the vapor phase times K1 times the mole fraction of benzene in the liquid phase. And then I'm going to rewrite the total moles in the liquid phase as the total moles from our feed minus the moles of our the moles in the vapor phase. And doing this, we'll get rid of another unknown that we don't know, which is the total moles in the liquid phase. So now I can factor out x1. And we can divide by this term to isolate it on the right side of the equation. And that gives this expression here, and I'm actually going to factor out the moles of vapor to simplify this expression a little bit more. And now we can divide the right side by f to get rid of the f in the numerator. So I just divided by f, and now we can use this expression to plug in to this equation right here. So we get the summation of the mole fraction of benzene going into the feed times Ki minus 1 divided by 1 plus the vapor mole ratio of our feed times Ki minus 1. And so now this expression can be used from I equals 1 to n for any number of components to perform flash calculations. So from here, we know we were given this value. We can calculate K using the set temperature and pressure. So we know our values for K. We were given the moles of feed in, And so now we're just left with one unknown, and I'll use this to solve a flash calculation in the next video in Python.